Hello, and welcome to the third installment of the MotorDoc podcast. The focus for this part of the series is related to energy and emissions from your maintenance program. In part three, we're going to discuss, in effect, what you see here. We're going to be discussing belted applications using electrical signature analysis, in particular the EMPATH product. Later on, we're going to cover things like steam and compressed air and so on. But for this particular case, we want to take a look at something that's directly measurable that we can utilize to justify our maintenance practices, etc. And what's really kind of important about this is that in reality, there's not an increased cost. There is a significant return. So the basic application of proper maintenance payback is immediate. And the measurable values based upon how we perform maintenance and extend the life of the machine comes down to a measurable value at the P&L, plus the ability to then link that back to specific goals for the company. If your company has emissions goals or zero emissions goals in the near future, your maintenance program can impact in excess of 15%. The range can go as high, and we've seen this, as high as 50% of the total energy costs when things have not been properly maintained in the past. Now, if we're going from an active maintenance program to a precision maintenance program, then you'll see improvements ranging from 5 to over 20% reduced energy costs. That is a measurable value at the corporate level on the P&L. So getting into our discussion, what you'll see here, to me this screen's off to the right, so what you'll see here is basically how belted applications are identified. Now, this works in both electrical signature and vibration. However, we're using electrical signature to show the actual kilowatts. So we're going to look at a real set of data. The data was taken, again, relatively recently. The problem is it got worse, but that's neither here nor there. So when we take a look at this particular screen here, you'll notice that we take the belt length, and then we take the speed of the machine times the sheave. Basically, if we take it on the driven equipment, we would go off of driven equipment speed. I highly recommend you go off the driver speed because if there's slip, that driven speed is going to be a little different. I'll note the EMPATH system actually identifies the percentage of slip as long as the data is entered correctly. Remember, garbage in, garbage out. So anyways, in this case, in this example that we use in a lot of our presentations, 29.33 hertz, which is about 1785-ish, 1790. Anyways, that times 4 pi gives us the circumference. That comes out to 368.6 inches per second. Now I then use both of these to take that divided by the number of inches, and that gives me a frequency. So that 3.79 hertz belt frequency. What's particularly interesting, something I've been observing for a while, is I'm going to find that range, regardless of size, to not be too much different than this. It's going to be somewhere in the range of a couple of hertz to up to 10 hertz. Now, if I'm doing a size-to-size pulley, that's different. But in either case, as long as I'm taking voltage and current, I can then take a look at it. What else can I do with this? Well, if these exist, well, first off, I'll have a one-time. If I have a 2 or more time harmonic of this, that usually indicates belt flapping, right? So you'll usually see that in fan applications and so on, where there's turbulence, I'll get that flapping. The immediate response by most technicians is, must be a loose belt because I see the belt flapping, therefore I will continue to tighten it. The problem with that is I could end up with an overtensioned belt, which will damage the bearings in the machine. Now, what's interesting, when I start adding together all of the effects of overtension belts First thing I look for to see if it's overtensioned is if I have static eccentricity, which is, by the way, another loss. So if I have soft foot, I have anything like that, it's a measurable kilowatt value. In any case, if I overtension the belts, the bearings become pivot points as the shaft deflects in one direction, with the deflection being opposite of the fan where it's being pulled. Well, I'm going to, of course, have stresses on those bearings as a result, whether or not it's a roller bearing or a ball bearing. And then, of course, the opposite drive end. Same type of thing. That pilot bearing is not supposed to be carrying a load, but if I have overtensioned the belts, it will. So one, the other, or both can end up causing some problems and eventual failure. So when I start looking at my total losses, in addition to the belt losses, I can also look and see if I have additional bearing losses. That would be all components of the bearing. And if I have something related to static eccentricity. So if I want to impress my friends, I can say, okay, I have a belt frequency, I have multiple belt frequencies. Oh, by the way, it's overtensioned. I can tell that because of the static eccentricity. In the meantime, with electrical signature analysis, if it's in a fan application, I can usually tell why I have the belt flapping in the first place, and that could be cavitation or turbulence. So those are conditions that I'll take a look at. So let's get right into some real data. Get rid of this. Here's a real machine. This is what pops up. That's going to tell me I've got a belted application. We will go ahead and open this up. The calculator tells me what it finds, but I'll show you the data in just a second. So in any case, when I take a look at this, you'll notice it's identifying a belted related thing. We're also at a relatively high percentage load. I take a look here. I've got 109.1 input kilowatts and 101.2, which gives me a relatively good efficiency on the machine. And then there's other things that I can take a look at here. More importantly, I'm interested in the running speed, which is 29.785. So when I take a look at everything, and of course I don't have a bad bearing, which is good, let's take a look at the nameplate. Nameplate information. I'd entered in belt applications, hence it showed me a 1-time, 2-time. And there's actually a 3-time belt flapping, which is right here. So you can see that's a harmonic. So we're going to pay attention to the 3 points when we take a look at our data. And it actually looks like there's a 4th out here, about 31.5 hertz. So we're going to end up taking a look and seeing what the energy losses are associated with that belt flapping. And that all comes from those same calculations from here. Of note is that my other speeds appear to be, such as the pulley speed, appears to be not showing anything, meaning I don't have sheave wear. So once I have that and I know what my bearings are here, which of course is a roller bearing on the front and an opposite drive end, that is a ball bearing, we're going to go ahead and take a look at some of those. And knowing, of course, my rotor bars, I can say the running speed times rotor bars plus and minus 1-time, 3-time, and 5 times line frequency is going to provide me whether or not I have static eccentricity. So we're going to take a look at that as well. It's not bad enough that it tripped anything over here, but there may be energy losses associated with it if this is an overtension belt. So when we take, and of course, casting voids always happen in induction machines. You don't condemn a machine based upon that unless you're having some other problems. So we know we have these conditions here. Let's go ahead and pull back and see what else is going on in this machine. You can see there's a lot of additional peaks here. And let's see if any of those are associated with bearing tension. And I do not see too many peaks lining up. There's some that are close on the outer race, so that may be due to tension. We'll find out. And then let's go ahead and take a look at the opposite drive end bearing as well. And these are just running speed times those multipliers that we saw, and then plus and minus the around the line frequency in this case, until we hit 120 hertz, because this is 60 hertz. Above that, it's going to be side bands of line frequency with that multiplier in the middle. So if I were doing vibration, it would be the bearing multiplier times the running speed, and then all kinds of other things going on. Notice also around here, there's kind of a raised noise floor right under my line frequency. That will be some form of cavitation. Now, these are pumps, so that is going to be part of the reason why we have belt flapping. So what we need to do is make sure and see if these things have been properly tensioned to the application, or perhaps there may be some fatiguing or cracking in the belts. That's something to take a look at, or the belt application may be misaligned, but let's take a look. I don't have a high one-time pulley, so it's not on that side. And my running speed, one-time RPM, is about 70 dB down. I'm not above 60 or 65 dB down. So while it's got some possible misalignment, maybe a little unbalanced, nothing to basically say that that's causing what I'm looking at. So I've eliminated that. So let's go up and take a look at our higher frequency data set. Now the EMPATH is taking 12,000 samples a second, which gives me a Nyquist of 6,000. Now the nice thing is, because there's very little above 360,000 CPM, aliasing is not really too much of an issue. So we'll take a look. So one of the first things I look at, this is across 10 seconds. This opens up, it'll usually start at 0.05 down here, so I can see what the waveform looks like. I've got a nice balanced voltage. What I have here is kind of an oscillation. Now that will go with the belts, and that's part of the frequency I'm looking at. Very interesting. And the other frequencies that reside there as well. So let's take a quick look and see what happens as far as our static eccentricity. So let's get in power harmonics, because we want to ignore any of those peaks. Let's take a look at static. That's right here. And we'll zoom in so we can see what's going on. And you notice I don't have significant peaks down in voltage, but I very definitely have peaks up in current. That means that I have overtension belts. 99%. It could be that the rotor's off center, it could be soft foot, could be a combination of those things, but chances are, based on what I'm seeing, I've got overtension belts. Okay, so that's another loss we're going to look at. So when we take a look at losses next, we're going to add this. We're going to add in our bearing losses. So let's go ahead now, and we are going to take a look. And as you may remember, the total energy, consumed by the application at incoming power is about 109 kilowatts on this particular machine, which is a 150 horsepower machine. So we're going to keep out of there. We're going to use this as a reference. So the next part, what we do is we want to take a look at our kilowatts, which in the EMPATH system, there's a kilowatt analysis capability. So there's my RMS kilowatts, and there's my actual kilowatts for the machine. And here we go. Now first, I can analyze off of this and you can actually see that things are lined up, but I want the actual values. So we're going to go ahead and switch this over to our linear spectrum. And this will allow us to explore some of these things. So you notice this really a high 120 hertz. We ignore line frequency stuff as we're going through this. So let's take a look on one side of it. And we're going to take a look at the belted values. So the sheave is hiding in here somewhere. I'm not going to worry too much about that. So that value is 9.6 roughly, maybe just a little higher, but about 9.6 kilowatts. This one here is, we'll just call that 3.5 to make up for that little peak there. And then we have another one here. Let's go ahead and find about the center of that. I could also just as easily do this and just have it do harmonic cursors, and that'll give me the value. Oh, I want to go back here, don't I? I'll move those back here. There we go. And so at that value there, we are at 1.3 roughly. There's more peaks. Look at this. So there's one here that's at about a quarter kilowatt, and this one here is another. So that could be another third kilowatt. So that totaled up is going to give me 14.7 kilowatt hours. So I'll note that. Next thing we'll want to do is go ahead, and we'll get rid of this. Is come in here and we're going to take a look at bearing impact. So let's take a look at our bearings. I have the cage, which is there. There's nothing there, obviously. Let's pull back so we can get all the frequencies. Inner and outer race. We'll zoom in. There's my outer race there, and there is my inner race. The inner race is very, very low, so we'll discard that. So that's on my drive end. Move back again, and if in some cases that's going to be significant enough, we want to pay attention. So let's take a look in here and see what's going on this particular bearing. I have a bit of a ball spin. This is blended in with, oh, I'm sorry, that's not that. Yep, same type of thing. Very, very, very little energy being lost comparatively. So good news is what that also means is that that we can correct this sheave application. And there's the other one. So my inner race peak is not significant enough. This means that we can actually salvage this application and save these bearings. Next bit is we're going to go ahead now and take a look at that static eccentricity set out here and see what the impact is. Now there's my peaks lining up, and I am at a very, very low value. It's about 380 watts there. 10 watts, and then this one here is going to be about 220 watts. So that just adds about another tenth. So we'll say 14.8 kilowatts total. So it's overtension, but not too bad, especially if I compare it. So I'm at 14.7 kilowatts, which is more than 10% of the value of this. So it's a serious condition that I absolutely want to pay attention to. But let's go ahead and see what that impact is. So when I pull up my calculator, and let's say this thing's operating 8,000 hours per year, that's going to be 14.8 kilowatts times 8,000. That gives me 118,400 kilowatt hours, or 118.4 megawatt hours. divide it by 1,000 to get megawatt hours. So I'm going to use both of those values in our next bit. So first off, I do have a demand, an unnecessary demand of 14.8 kilowatts. So let's start with this first. Let's say I'm at 10 cents a kilowatt hour. That's really simple. Times 10 cents. That's $11,840 for just usage cost. The demand cost is going to, let's say we're at $10 a kilowatt. That's going to be 14.8 times 10. Now, mind you, there's time of day and there's all this other stuff. You know, it can definitely be more complicated than this. We'll do that in another episode. I'm trying to keep these relatively short, and that's not happening. So $148 times 12 months. That means that my demand charge is going to be another $1,800 roughly, or $1,776. Good year. And I'll add in $11,840. So that means right off the bat, that's $13,616 that improperly tensioned belt, possibly worn belts, are costing me per year. And by the way, belts don't get better. So as the belt begins to wear, as the bearings begin to fail, and the other components that are associated with it, let alone the bearings on the driven equipment, as all of that begins to be affected, this cost will continue to increase. So the number I'm using right here is the conservative value. That means I'll affect that energy bill by that much. Now, if I'm talking about a plant that's in the high megawatts, this first one, that might not show that significant an impact at the utility bill. But as I start correcting these, like this particular application has multiples of these machines, as I start correcting that, it will literally show a gradual decrease in energy use. And we'll talk about how to determine that in a future episode. As a matter of fact, we'll use this data when we do next week's episode, which will be to dive in a little deeper. But just for a quick, rule of thumb type thing, we're right there. We got a conservative value we can work with, and let them know. Now, here's the next part. If we use the national average, so let's clear this out, and we are at 118.4 megawatt hours, well, that has an impact too. So what does 118.4 megawatt hours have an impact? Well, in the national average, when I am doing mitigation, when I'm fixing things, I can use from a national average 0.709 metric tons of CO2 per megawatt hour. For different areas, that varies a little bit. Some are a little lower, some are a little higher. That's the mean. It rarely drops unless you're taking pure renewables, which nobody right now, even if you're buying pure renewable, nobody's actually using pure renewable. That can go as low as, say, 0.481. So in a region like here where I've got primarily nuclear and a lot of wind and then and less base load, we're at that, about 0.49, about 0.5, somewhere in that area. But we can use the tools we talked about in part 2 for that. So we're going to use the national average. So 118.4 times 0.709 gives me 84 tons, 83.9 or 84 tons, metric tons, and there's 2,204 pounds per ton, but I'm going to use this value. That means that one pulley, that one sheave, that one mistensioned belt, because, we needed to hurry up and not spend the extra 10 minutes tensioning the belt, or we came back and we said, you know what, let's flap it a little bit. Let's go ahead and get rid of that flap, and we're going to increase the load on our machine, and we're going to generate another 84 tons of CO2 per year. If you have an emissions goal, this is a measurable amount. you will be able to report this back as well. And to take that one step further, we can definitely go in to the calculator, US EPA. So this gives you the ability to report this to your management, right? So we're going to go off of energy data. We're going to come here. Now, kilowatt hours used, we're not using that because we're not totaling it up. Instead, we're going to use kilowatt hours avoided. This is the higher value. It takes it off the base, right? And we're going to say that is 100 and I think I have this right. 118,400. If it's ridiculously high, then I should have entered in megawatt hours, but this is kilowatt hours, right? So 118,400 kilowatt hours avoided. And I click that, and that's going to tell me 83.9 metric tons. I can convert this over and say pounds if I want, which ouch. But let's go back to metric tons. So we're going to say this value. I always use this value here because it's more digestible. But you can then see that removes the equivalent of 19 pure gas cars off the road, or equivalent of 215,000 miles, which is about a year's worth of driving for me, or 9,500 gallons of gasoline. So these are the equivalents, basically what it would do otherwise. So these are the avoidance things. This is something that you can then print or provide to management, print and post up, whatever you need to do, because it is directly this value here. So again, as I mentioned before, you'll notice this warning on top. This is not meant for emission inventories. This is meant for avoidance, right? So, or reduction, I should say. So they always say that you use this for reduction. When I'm looking at total inventories, that's completely different. Those values are going to be a little bit smaller, but it would still be at least 40 tons for this belted application. So if I've given you a little insight and a few things to consider, I know I went well beyond the 10 minutes that I said I was going to try to do these, and of course I don't think I'm ever going to match 10 minutes. But in any case, next week what we're going to talk about is a slightly deeper dive into this, how we're getting all these numbers together, and what we're seeing here. We'll work off of this particular demonstration, and then we're going to move on to a couple of other things. I'll do one in a couple of episodes to change things up on compressed air, because then I can use both. I can use an air issue and the other. So next week we'll be on a tool called Measure, MEASUR. If you're interested, look it up. It is a free software by the U.S. Department of Energy that utilizes this information and allows you to look at scenarios and gives you opportunities based on all fuel types and all energy use in a plant on what the impacts are by performing certain actions. With that, thank you very much and have a great day.